Today, I'll be adding shaders, textures, clouds, and an atmosphere to my randomly generated planets to make them look as photorealistic as possible, and at the end of the video, we'll even make them look authentic from orbit. But the first step is improving the resolution. My planet is split into chunks, similar to Minecraft, and ideally every chunk would look like the one on the left, but the right one is a lot more efficient for the computer to store and display. However, when they are far away in the distance, these two look almost identical. So what if we create multiple levels of detail of the same chunk, and as it gets further and further away, we switch between them in a way almost invisible to the eye. The only problem is we'll eventually run out of pixels to remove. So instead we can just fix the resolution and make the chunks bigger the further away they are. And here's how we'll do that. Let's say the player is right here. These are our chunks, but right now they're way too big. So we'll draw a circle around the player, and for every chunk inside this circle, we'll split it into 4 chunks of the same resolution, but half the size. And we don't have to stop there. Now we can make the circle twice as small and once again split the chunks that are inside. We can just keep doing this, and as the chunks get smaller and smaller, they cover less area with the same amount of tiles, so they seem a lot more detailed. Here I've implemented that onto my planets, and now the chunks right next to the player are really small, but once we start zooming out, you can see that they get bigger and bigger the further away they are. And this is what it looks like from the point of view of the player. We can see that the resolution decreases with distance. Obviously, I kept the overall resolution very low to exaggerate the effect for now, but in the end this should be almost invisible to the player. One problem is that now there are small gaps in the terrain on the points where 2 different resolutions meet. In reality, the mountain has a smooth shape that we'd only see with infinite resolution, but our chunks sample only a few times per chunk to approximate the shape. The lower resolution version has even fewer points, so it approximates less accurately, and the holes that we see are the gaps between these 2 approximations. Thankfully, the fix is very simple. Since the gaps are very small, we can just add a small skirt around every chunk by copying all the border points and dropping them down to fill the gaps. And now that there are no more gaps between chunks, the visuals look a lot better. But we're far from done. The next step is getting rid of this blocky look entirely and making the planet fully photorealistic. But before that, I want to show you something cool in this game that I've been playing recently. I love it when different gaming universes come together and create unique events that stay in your memory for a long time. Raid just launched a crossover with Assassin's Creed, and the visuals honestly surprised me. They added 5 legendary assassins to the game: Ezio Auditore, Edward Kenway, Bayek, Basim, and Cassandra. The best part is that you can get Ezio for free just by logging into the game for 7 days, and if you keep logging in after that, you'll also get extra gear to help and get up to speed quickly. There are also additional ways such as dedicated events, tournaments, and summon boosts to obtain the other assassins. Right now is the perfect time to start playing because Raid is celebrating its 7th anniversary and they're giving out a ton of free rewards. If you download the game using my link in the description or scan the QR code, you'll get a $200 starter package, including the legendary champion Krokmar the Devourer, epic champion Galapo the Recluse at level 25, and a lot of other valuable rewards on the screen. New players can also unlock the legendary champion Pelops the Victor using the promo code RAID7, and if you want a different legendary champion, there are 6 other promo codes, but you can only choose one, so choose wisely. But that's not all. Both new and existing players can get Pelops the Victor to the Classic Fusion event until March 21st. You can also claim plenty of rewards from the 7-day gift chain and earn a unique 7th anniversary avatar frame from the Titan event. So don't miss your chance. Click my link in the description or scan the QR code on the screen and get 3 legendary champions and many other anniversary rewards. Thanks Raid Shadow Legends for sponsoring this video. And now let's get back to making these planets look photorealistic. Before adding textures, I have to fix the shading, which is broken at the edges between chunks, and it's really making the planet look jagged. This happens because each chunk calculates its lighting independently, but to compute the shading correctly, a chunk needs to know the shape of its neighbors. So we will have to send that data over somehow. And to do that, I made a quick tool that for a given chunk finds all of its neighbors. And when calculating the shadows, we will also take into account the shapes of those chunks. With that in place, we can fix the shading at the seams. Now that the planet looks like one continuous surface instead of a collection of pieces, it's time to get rid of the blocky Minecraft look using something called a fragment shader. Right now our chunk is split into tiles and we calculate the color of each one while the chunk is being generated. That means that all of the math runs on the computer's CPU as part of the generation step. The problem with that is that this work happens sequentially. This means that the CPU finishes computing one tile before moving on to the next. And this is where a fragment shader comes into play. Instead of pre-computing the color and storing it in a texture, we'll move over to the GPU and calculate the color of every single pixel that's actually on the screen for any given frame. We'll use a shader which, for each pixel, finds the point on the chunk that it's showing, takes the data about that point like its position and slope, runs it through a set of instructions, and spits out the color. The best part about the GPU is that it does this for every single pixel on the screen all at once. But how do we give the instructions to the GPU? We will use something called shader graph, which is a visual way of doing math operations and sending the results to our shader. For example, we can set the color of every pixel to the same color, and this is how that looks on our planets. We can also change the color really easily now because everything is being calculated during rendering. But shader graph offers us so much more, like addition, multiplication, and most importantly, linear interpolation or lerp. This operation takes in 3 inputs, a minimum and a maximum value, and a number between 0 and 1 that acts like a slider between those values. When the slider is 0, the output is the minimum. When it's 1, you get the second value, and anything in between smoothly blends from one to the other. The tricky part is figuring out what number between 0 and 1 we should use for that slider. That's where inverse lerp comes in. Inverse lerp does the exact opposite of lerp. If the slider is equal to the minimum now, the result is 0. And as it goes to the maximum, the output blends to 1. Now, we can use anything as the input for the inverse lerp, like for example the height of each pixel. In that case, the minimum and maximum become a range of heights, and inverse lerp will map any pixel to a number between 0 and 1 based on how high it is. Now we can feed that number into our regular lerp and make it blend between colors. So everything below the minimum height becomes the first color, everything above the maximum height becomes the second color, and the terrain in between smoothly blends from one to the other. And this is what that looks like on the planet. We can now play around with the starting and ending colors, as well as the maximum and minimum height. And as you can see, we can quickly get to something that's starting to look like grass and mountains. Now, if we replace the height of the pixel in the inverse lerp with the angle between the terrain at that point and the up direction, we can instead color the terrain based on how steep it is. And this is going to be super useful since we can now combine these two shaders in order to create our master terrain shader. We'll take the highest points using the first shader and turn them into snow. Then we will use the second shader to find the steep parts, and that will be rock. This is already looking super cool, but right now it can only display grass as the ground, when in reality our planet is covered with many different biomes. So, the shader needs to know where each biome should go. But the problem is that the biomes are calculated earlier during the generation step, and we only decide them once per tile, not for every single pixel. Luckily, while generating the mesh, I can assign a color to every vertex, and the GPU will automatically blend the vertex data across every triangle. So whenever two biomes meet, the transition becomes smooth for free. Now, just sending the final color of each biome to the shader works, visually. But the moment we do that, the shader loses all other information about which biome is actually there. It just knows the color. And that means we wouldn't be able to apply different textures to different biomes later on. So instead we do something much smarter. Every color consists of 4 built-in channels: red, green, blue, and transparency. But instead of using them as a color, we can use them as 4 different biome weights. Let me explain. When generating a chunk, first I will look at which biomes appear in it and assign each biome to one of the channels. Let's say forest is the red channel and desert is the green. If a vertex belongs to the forest biome, I set red to 1 and everything else to 0. If it belongs to desert, only green becomes 1. It might look like we're sending random colors to the shader, but we are actually giving it all the data it needs to know the biome mix at each pixel. Now, in the shader, we can simply take each channel individually and multiply it by its biome's color. And then we add the results together. Since only the correct biome channel has a value of 1, that color is the one that remains. And just like that, the shader now knows exactly which biome exists at every pixel. But this is where it gets really good. We are no longer limited to flat colors. it's time to add textures. Since the planet is a sphere, we'll use something called triplanar sampling to apply the textures. It consists of just slapping a texture on each face and then smoothly blending between them. This generally looks surprisingly good. Now we can just pick a texture for each biome. These are the ones I went with. And instead of multiplying by the biome's color here in the shader, we multiply by the sampled triplanar texture. I've also added some textures for mountains, snow, and beaches. And this is what our planet looks like right now. And while it certainly looks a lot better, one problem is that the ground is very flat at the moment. And we can partially fix this using something called a normal map. This is a secondary texture that tells the shader how to calculate the shadows in order to fake a feeling of depth. And this already looks much better. Well, at the bottom half of the screen. It's finally time to add something that you guys have been suggesting for months: clouds and an atmosphere. In order to simulate clouds completely realistically, we would have to model them in full 3D, which is extremely complicated, and that would absolutely destroy performance. But if you'd like to see someone attempt that, I highly recommend this incredible Sebastian Lake video. For this project though, we'll use a much simpler technique that still gives great results. I started by creating a cloud texture in Photoshop, and I made sure that it tiles smoothly. Then I placed a giant sphere surrounding the whole planet and used the texture to control its opacity. So wherever the texture is white, we get clouds, and wherever it's black, the sphere is transparent and the sky stays clear. This gives us a good starting point, but the pattern is very repetitive. So instead of just using one texture, I use three: one large one and two smaller ones. By multiplying them all together, clouds only appear where all three layers overlap, which creates much more natural looking shapes. And down on the planet, they look even better. Next, I can slowly slide the textures over time so that the clouds actually move. And I also made the brightness react to the time of day so they still look good at night. Finally, when the sun sits behind the cloud in real life, the cloud grows brightly around the edges. So I added some extra lighting to the clouds when the sun is near them to simulate that effect. And with that, the clouds finally start to look believable. So we can move on to simulating the atmosphere. This is the change that will actually make the planet feel alive. And to achieve it, we'll have to change the color of the sky. And what better way to do that than to turn the sky into an even bigger ball surrounding the whole planet and the clouds. Now the sky isn't just a background color, it's something that we can control with a shader. That means that we can smoothly blend from a bright horizon to a deeper blue overhead, just like in real life. Now for the important part: sunsets and sunrises. The iconic orange glow appears because when the sun is near the horizon, the light has to pass through more of the atmosphere before reaching our eyes. Most of the blue light gets scattered away, leaving behind the warmer tones. So let's simulate that. For every pixel in the sky, we will calculate three values between 0 and 1. The first one is how close the sun is to the horizon. And since this one only cares about the sun and not the individual pixels, it will be the same across all of them. The second is how close the pixel itself is to the horizon, and this one will give us a nice gradient towards the horizon. And the third one is how closely the pixel aligns with the sun's direction. Only when all three conditions are satisfied should the sky glow orange. So we will multiply them together. That isolates exactly the part of the sky where a real sunset would appear. Now we can use that to blend in a warm scattering color with our sky blue, and we have ourselves a first real sunset. I haven't implemented the night yet, but luckily that's pretty easy to do by using our first criterion to transition to black once the sun is fully down. We can also slap on a simple star texture to give the night sky some more life, and after adding some more glow to the sun, this is what our fully finished sunset looks like. We are still missing a moon though. Luckily, in my last video I made a fully realistic moon generator that lets us shoot meteors at a random moon and export it. So here it is orbiting the planet. I've made it so that it's only visible during night or when it's super close to the sun. So technically, if you wait long enough, you could see a solar eclipse. Not this time though. For a few finishing touches, I've added a slight twilight color before a sunrise, and the terrain fog now realistically reacts to the time of day. There is one last thing I want to add today which will really take the look of my planets to the next level, and that is post-processing. This is a final adjustment step that happens after the rendering is complete, and it essentially acts like applying an Instagram filter, but with a lot more freedom. So after playing around with the settings for a while, I ended up with this post-processing volume, which makes the colors more vibrant, the nights deeper, and the overall visuals much richer. We still have to improve the orbit view, but just as a reminder, this is what we started with, and this is what we have now. And for those of you worried about performance, because of all the optimizations we added at the start of the video, this is still running at 150 frames per second on my laptop. I'm really happy with where we ended up, especially with the mountains and sunsets. But don't click off just yet, because now it's time to make the planets look photorealistic when viewed from orbit. All of the changes that we added so far kind of broke our space view. Luckily, the fixes were pretty straightforward. Now, the first thing I want to improve are the clouds. From orbit, Earth's clouds look very different. The most noticeable shapes are the large swirling cyclones. So I created a new cloud texture specifically for the space view that has a lot more twisting patterns. I also disabled post-processing for now since we'll need to adjust some of the settings, but the most obvious issue right now is the visible lines between some of the chunks. This happens because our terrain shader only has 4 color channels available, but sometimes a chunk can contain 5 or more different biomes. When that happens, my system falls back to a simpler technique where it just sends the biome color instead of the texture. On the surface, this will almost never happen because chunks are small, but in the space view, the chunks cover huge areas, so they often contain many biomes. Luckily, from space, the terrain textures are too small to see anyways, so the solution is simple. When viewing the planet from orbit, we always switch to simpler color shader. Now we can turn the post-processing back on with the settings set specifically for space. After slightly darkening the shadows, this gives us the final look of the planet. With the visuals now in a good place, in future videos we can focus on improving the realism of the terrain and climate simulation. For now, I added all of the new features to the generator app, so you can enable or disable the clouds and adjust how high above the ground they appear. You can also try out all the different shaders and, as always, play around with all the other generation settings. But the best new feature is that thanks to the Quadtree Chunk system, you can now watch your changes being applied live as the depth of the quad tree gradually increases. And once the generation is complete, you can choose which part of the planet you'd like to explore, and after a short wait, you get to experience all of the graphics improvements for yourself. As always, the app is available for free on my itch page. It will be the second link in the description. There is an optional donation, but of course you're free to click no thanks and the download will start anyway. I'd like to give a huge thanks to my Patreon supporters and Raid Shadow Legends. Without them, videos like this, which take months and months to make, wouldn't be possible. If you enjoyed this one, make sure to leave a like and subscribe so you don't miss the next video. And don't worry, it should take less than 7 months to make. Hopefully. Oh, and before you go, don't forget to download Raid Shadow Legends using the link in the description or scan my QR code to grab your free legendary champion and a bunch of anniversary rewards.